Alright, so today we're going to learn about implicit differentiation, which is different than explicit differentiation, which is what we've been doing so far. It's not much different though, so it's just going to add one slight little detail using the chain rule, which we already know. So before we get into the implicit differentiation, I want you to find the derivative of x squared plus y squared equals 25. Pause the video, unpause when you're ready to check your work. A hint is that you will need to solve the equation for y first. Alright, so first we need to solve for y. We get y squared equals 25 minus x squared. Take the square root of both sides, don't forget plus or minus. Y equals plus or minus the square root of 25 minus x squared. Now we can take the derivative, so dy dx, using the chain rule, bring down the 1/2. 25 minus x squared to the negative 1/2 times the derivative of the inside, which is negative 2x. Simplify. The 2 and the 1/2 are going to reduce. The negative is just going to make this still plus or minus. So the negative here does not affect the problem, and I get x over the square root of 25 minus x squared. That is my dy dx. So that was using what we call explicit differentiation. So we've been doing explicit differentiation or explicit derivatives, meaning y is defined in terms of x. So although the original equation here, y was not defined in terms of x, we were able to solve for y in terms of x, and then we could do explicit differentiation. So we can do explicit differentiation with y equals 1 over x squared, because this is x to the negative 2, so y prime is negative 2 x to the negative 3 or negative 2 over x cubed. We can do explicit differentiation with y equals 2x cubed plus 4x. This we just use our general power rule, so we'll get 6x squared plus 4. So these are all examples of explicit differentiation. If you can solve for y in terms of x, most of the time you want to do so because explicit differentiation is going to be a little bit simpler and quicker. What if you can't though? So sometimes we can't solve for y in terms of x, so then we have to do what we call implicit differentiation. So when we do implicit differentiation, all of our derivative rules still apply, but whenever we take the derivative of y, we're going to use the chain rule. So let's look at what's going to happen here. So if I take the derivative of this equation, the first term, that's all in terms of x, so I just take the derivative like I would. Because specifically, let me say this. Let's take a step back. What we're doing is we're solving for dy dx. And so since we're solving for dy dx, any term that is just an x, we can take our normal derivative. Any term that's a y, we're going to use our same power rule, so this will become 3y squared, but then times the derivative of y with respect to x, which is dy dx, and then plus 3 times the derivative of y with respect to x, dy dx, equals 0. So that's what we want to notice, that anytime we take the derivative of a term with a y, we have to treat it, or we have to use the chain rule. So we take the derivative of the term, so I use the power rule, I brought down the 3, y, reduce the power, times the derivative of y, which is just dy dx. Now we want to isolate the dy dx. So we'll get negative 3y squared dy dx plus 3 dy dx equals negative 6x squared. I can factor out a dy dx. And now divide by negative 3y squared plus 3. So we end up with dy dx is 2x squared over y squared minus 1. So notice that now dy dx might have y in the origin or in the derivative. So if variables agree, then we can use explicit differentiation. So if we're finding d dx of x cubed, we can just use explicit differentiation, and this is just 3x squared. That's when the variables agree. If variables disagree, so if I want to find d dx of y cubed, then I use implicit differentiation, which again is just using the chain rule. So we do everything the same as explicit differentiation, except for then we're also going to have a dy dx. So this will be 3y squared dy dx. So this is the difference between explicit and implicit differentiation. So now I want you guys to do some examples. Find d dx of x plus 4y and find d dx of x times y cubed. So the first one should be straightforward. The second one you will have to use the product rule. So pause the video, unpause when you're ready to check your work. Okay, so we don't need to really simplify anything here. We can't really do much because we're not solving anything. But d dx of x plus 4y, well, d dx of x is 1, and d dx of 4y is 4 times the derivative of y, which is dy dx. d dx of x times y cubed, I take the derivative of the first, so the derivative of x is 1. The second term stays the same, so that's y cubed, plus the first term, x, times the derivative of the second, so the derivative of y cubed is 3y squared dy dx. Alright, now I want you to find dy dx of the problem that we did at the very beginning, but now I want you to use implicit differentiation. So pause the video, use implicit differentiation, unpause when you're ready to check your work. Alright, so if we take the derivative using implicit differentiation, we bring down the 2, I get 2x, plus I bring down the 2, I get 2y dy dx equals 0. If I solve this for dy dx, I get dy dx equals negative x over y. So using implicit differentiation, this is what I get as a result. Now let's compare that to what we got in the original problem. We got dy dx equals plus or minus x over the square root of 25 minus x squared. So let's discuss the difference a little bit. Well, our original one we had plus or minus, here we just have minus. What's the difference, or where are we lacking the plus or minus? Well, think about where the plus or minus came from. The plus or minus came from when we solved the original equation for y. So if you were to go back and solve this original equation for y and substitute that in here for y, you're going to end up with dy dx equals plus or minus x over the square root of 25 minus x squared. So it is the same thing. Next example. Determine the slope of the tangent line to the graph of x squared plus 4y squared equals 4 at the point root 2, comma, negative 1 over root 2. So pause the video, find the slope, unpause when you're ready to check your work. Alright, so we should end up with the slope of the tangent line at the point is 1/2. But let's look at how we get that. So first we find the derivative. We're trying to solve for dy dx because that is going to give us the slope of the tangent line. So the derivative, I get 2x plus 8y dy dx equals 0. Solve for dy dx. dy dx is negative x over 4y. Now I just plug the point in, so root 2 for x, negative 1 over root 2 for y. So dy dx of root 2 comma negative 1 over root 2 is negative root 2 over 4 times negative 1 over root 2. The negatives cancel, I multiply by the reciprocal, and I end up with 2 over 4, which is 1/2. Okay, now I want you to try the same example, but use explicit differentiation. So pause the video, find the slope, but using explicit differentiation, unpause when you're ready to check your work. Alright, so if we take the derivative, or if we find the slope using explicit differentiation, we end up with plus or minus 1/2. So that's slightly different than what we got with the implicit, because remember with implicit, we ended up with just 1/2. So how do we know using the explicit if it's the plus or the minus? So see that this was a lot more work. Well, first let's go through the work. So first I need to solve for y. So I subtracted x squared, I divided by 4, I took the square root, I simplified a little bit here, so you could leave it how I have it in the blue here. I simplified it to the purple. Either way, it doesn't matter. So then we take the derivative. So y prime, I bring down the exponent, leave the inside, subtract the exponent by 1, take the derivative of the inside using the chain rule, simplify a little bit, and I get y prime is plus or minus x over 2 root 4 minus x squared. Now I plug in root 2 to evaluate the slope at root 2, and that's how I end up with the plus or minus 1/2. So again, how do I know if it's plus or if it's minus? Well, it goes back up to when we were solving. So at here and here is where we determine the plus or the minus. Since this point is below the x-axis, then we're going to use the minus. If it was above the x-axis, then we would use the plus. But what that means is we're using the minus at this point before we take the derivative. So my actual equation is going to be y equals negative 1/2 root 4 minus x squared. So now when I take the derivative, y prime equals negative 1/2 times 1/2 times 4 minus x squared to the negative 1/2 times negative 2x. Now because of this negative and this negative, the slope is going to end up being the positive 1/2 when I plug in the root 2. So it still does work out, but it's more work and it involves a little bit more thought. Alright, last example, I want you to find the equation of a tangent line at negative 1, 2 for the equation y to the 5th plus 6xy minus x to the 4th y squared equals 16. Pause the video, unpause when you're ready to check your work. Okay, so the equation to the tangent line at the point negative 1, negative 2, at the point negative 1, 2, should be y minus 2 equals negative 2/5 times the quantity x plus 1. So let's look at how we get that. First we do the derivative. So the derivative of y to the 5th is 5y to the 4th dy dx. The derivative of 6xy, I have to use the product rule. So the derivative of the first is 6 times the second, which is y, plus the first, 6x, times the derivative of the second, dy dx. Now I have to use the product rule again. Because of the negative, both terms are going to be negative. So it's going to be derivative of the first, 4x cubed, times the second, y squared. The first, x to the 4th, times the derivative of the second, 2y dy dx. Now we want to group the terms that have a dy dx, bring everything else over to the other side, factor out the dy dx, and divide by the remaining terms. So dy dx is 4x cubed y squared minus 6y over 5y to the 4th plus 6x minus 2x to the 4th y. Plug in negative 1, 2 to find the slope, and that's how I come up with my tangent line. Here's your conclusion. Remember, implicit differentiation is when you do not have a function y in terms of x.